Good afternoon. The reason you're watching this today is because I'm at the courthouse where I got called to do jury duty, and I wanted to at least make a quick video to keep you going with the notes that we have from Chapter 5. This chapter deals especially with segments that come up in triangles, and we already talked about mid-segments. The next section deals with the idea of bisectors. Bisect, you remember, means cut in half, and you can bisect either an angle or a segment. We're going to talk a little bit about both of those. So first, I want to introduce a term that is important in this section. It's the term equidistant. And if you just look at what that word means, you should be able to get the idea of equal distance out of it. Equidistance just means the same distance from. So I might say, for example, that Clear Lake and Fort Dodge are equidistant from Algona. Another term that comes up in this section that's sort of common sense, but you want to make sure that you know, is the term distance. And it says here that the distance from a point to a line is always the shortest possible distance. And if you want to get the shortest possible distance, what you have to do is go perpendicular. You go straight up and down and make a right angle. You don't jog off of that anywhere. It's just a straight segment perpendicular to the line. It's basically like saying if I was on Highway 18 and I wanted to go up to Bancroft, the shortest way to get there is to go up Highway 169. You just go straight up the highway, perpendicular at the four corners, and that's the quickest way to get to Bancroft. You guys might remember that for a lot of this year, there was a bridge out and there was a big detour that you had to take. That took you out of the way, and so you went off of the shortest distance. The distance is always perpendicular, and it's always the shortest way there is to get from one place to another. That leads into the first rule we're going to learn about bisectors and triangles. It says if a point lies on the perpendicular bisector of a segment, then the point is equidistant from the endpoints of the segment. And so you can see we have a perpendicular bisector here. And what this is saying is that point A is the same distance from both B and C. I'm not going to go through the whole proof of this, but the reason why that's true is that you end up making an isosceles triangle. You end up with triangles that would be congruent by SAS, and that's going to end up making those equidistant. So of course, when you get into your problems, you're going to see things that look kind of like this. We have a perpendicular bisector here, and you can already see that point L is equidistant from M and P. The question here is to find X, and the whole point there is that point Q at the bottom is going to also have to be equidistant from M and P. And like a whole lot of things that you've done in geometry, what that boils down to is you've got to set stuff that looks equal to each other. Here we'd have 4x plus 3 equals 11. And if you go ahead and solve that, that would mean 4x equals 8. So x is going to have to be 2. So here it's just saying that if you turn things around and you do the converse, you also get a rule that works out. If a point is equidistant to two endpoints of a segment, then the point lies on the perpendicular bisector of that segment. I'll pause for just a minute in case people do want to jot that down. That again happens because we end up with some congruent triangles. Here you would end up with triangles that are going to be congruent by HL, and the corresponding parts are the two halves of segment AB. Another quick rule is this one. It's what's officially called the angle bisector theorem. And it just says that if a point is on the bisector of an angle, then it's equidistant to the two sides of the angle. So if I drew a point anywhere on BD, the bisector of the big angle I have here, then it's going to be the same distance to get to the side that's at the top and the side that's at the bottom. Those have to be the same distance. If a point's on the bisector of an angle, it's equidistant from the two sides of the angle. And again, most of the problems you're going to see are largely common sense ones. There'll be things like this where the directions would ask you, how big is LM? And because M is on the angle bisector, it's got to be the same to the bottom as it is to the top, even though this picture is not really drawn right. And it would end up being 12.8. Here's the same idea, but with a little bit more complicated problem. Here, the directions say find X. And so, of course, what you want to do is to set the expressions that you have equal. If you do that, you're going to end up with 2 times x minus 1 equals 3x minus 11. You get all your x's on one side, all your numbers on the other, and it does turn out that x has to be 9. You can also turn that theorem around and do the converse. The type of problem you might see with this will tell you that the two segments are equal, and it's going to ask you how big one of the halves of the angle is. And again, the important thing is those have to be the same as well. If a point's on the interior of an angle and it's equidistant from the sides, then it has to be on the angle bisector. Now, I know I went through that pretty quickly, but if you missed something and want to listen to it again, it's all linked from Google Classroom, so you can watch the video on your phone and again at your leisure. But again, a lot of the problems you're doing really are just telling you that if you have stuff that looks the same, yeah, it's going to be the same when you have special segments that come up in triangles. With that, we'll sign off for now, and hopefully we will see you tomorrow.